So Pkt6, class 17, and Friday. So we had an issue today. No matter what I did, it would not share the screen. The only way I got it to work was after we were done, I shut down my computer, shut down the iPad, restarted everything up again, and then it worked. So I'm going to have to just do a recap without any audience unless somebody joins in accidentally. All right, so here we go. I'll go through this rather quickly since there won't be much discussion. We did do Flashback Friday today. We got that in at least. He didn't need a. We went ahead and we met with the virtual kids, and I met for like 45 minutes, but it just there wasn't any kind of sharing of screens. So there's a lot of waving of the arms. I don't know if it was effective or not. All right, so the homework I go around and check in class was number 2 on 6.4. So make sure the front of 6.4 is done. There it is. Okay, so we started off going back and talking about Newton's third law again, and it was because of this. Felix Baumgartner jumping from a gondola. This is a few years ago. You may have seen it when you were much younger. He attached himself to a Mylar balloon, and I have if I remember, I'll attach a video to this in the comments. But he went up to something like 122,000 feet, somewhere in there, above the Earth, and then jumped. As he stood out, you can see the curvature of the Earth. If you look a long distance shot, he's up there. It's very cold up there. There's no air. You're looking down. You're looking up above you. You see stars. It's the middle of the daytime. So he's way above most of the atmosphere. And then he steps off. It's one of the bravest things I've ever seen happen. He did pretty well. He said that he looked back and he felt like he was sitting still, like he was just suspended in space. He looked back up and saw the gondola flying away from him, like about 600 miles an hour. It just seemed bizarre. Then he realized, wait a minute, he was the one moving. Good example of relativity, Galilean relativity, anyway. So he did fine. He broke the sound barrier really fast since there's no air up there. There's no air drag. And then as he got into the down into the thicker atmosphere, he had to be very careful because he's going so fast. It slows him down, heats him up, but kind of like re-entry of a spaceship. Anyway, his foot got off a little bit. His foot got angled out, and he went in. It acted like a rudder, and he went into a tailspin. He spun around, passed out. He went into I don't know what his omega was, but a lot of revolutions per minute, and like a wash machine. And blood left his head, passes out. Does manage to come through, and then pulls the cord and comes back down to Earth. But pretty exciting. You should watch it. Kittinger was the guy on the ground. The Kittinger was the guy before him back in I think it was 50s that jumped, had the old record, but Baumgartner beat that record. All right, so we talked about Baumgartner, and the question was, if he is up there jumping out of a gondola, he has, of course, mg on him, and then the Earth is down here. Okay. So now that's not the same. Call it mg prime because it's a slight different. Someone said in class, well, the reason why there's no gravity on him up there. No. There's plenty of gravity. It's just lessened slightly. I mean, on Earth, it's 9.81. Up at that height, maybe 9.79. We have the table. We could look at it, maybe 9.78 at the most. Doesn't drop much. So the question is, Newton said that every force in the universe has a component force which cancels it. It has a canceller. So you're always canceled no matter what you do. There's a force that opposes everything you do. That always bothered me, but I guess now it's just Newton's third law. It's true. There's nothing I can do that doesn't have a counter force. So I'm thinking here, maybe I found a way for there to be a single force, right? By itself. like there's a similar thing in electromagnetics, which says there are no monopoles. If you look it up, things are always dipole, positive, negative end. There's nothing that just has that. If you have a positive end on your particle, you'll have a negative end. Those are called dipoles. But monopoles is just one charge. Nothing has that. That's um, a molecule, whatever. You don't have things that aren't dipoles. Same kind of thing here. You don't have a force in mechanics without an opposing force. So I asked the virtual kids, where is the opposing force to the mg? And finally, usually somebody will say, well, wait a minute, isn't he pulling the earth up to him? And I say, ha, 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 that's ridiculous. How can that possibly be? And then I agree with them. So Felix Baumgartner is being pulled down to earth by a force. And at the same time, the exact same force is pulling the earth up to Felix Baumgartner, or any kind of skydiver. Or if you jump off a chair, when you are free falling, the earth is being pulled up to you. And so that sounds crazy, but we have, if we go forces, mass times acceleration. So I have the force of, say, Felix is A and the earth is B. I have the force of B on A, the force of the earth on Felix, and that equals to the opposite of the force of Felix on the earth, is what I'm saying. Well, in that case, force is equals mass times acceleration. But in Felix's case, his mass is really tiny. And then he has to have a huge acceleration to make up for the fact that the mass of the earth is so big, so much bigger, then it has a tiny acceleration. See, the forces can be the same, but because the masses are different, the acceleration. So Felix would not accelerate the earth towards him very much. So then the question came up a few years ago. They said, well, what if everybody jumped? And so he said, okay, what if every man, woman, and child, and we throw in the cats and the dogs and the goats, and we put everybody up in a plane, and then they all jump. This is, by the way, this is called a Gedankt. This is a thought experiment, pondering. It's a German word that Einstein used to use. So we're pondering, what if everybody jumped out of a plane? Would that then be enough force, attraction of the earth to make the earth move? And when we did the math here, let's see, got it somewhere here. Somewhere, maybe here it is, way down here. If we do the math on that from a couple of years ago, we guesstimated about 70 kilograms per person. We said about 7 billion people. I guess we were throwing in a few cats and dogs. And we got a weight of 5 trillion newtons would be how much weight they have to attract or 5 times 10 to the 11th kilograms for mass to attract the earth. Well, the earth has a mass of 6 times 10 to the 24th. So when you do the math on that, you find out that the earth is accelerated towards all the people that jumped out of the plane. It's accelerated at about 1 picometer per second per second. That's 1 trillionth of a meter per second, which is unnoticeable. So basically, it would not make the earth budge. Now, the one thing that does kind of make the earth bulge and budge is the moon. The moon's got a mass of around 10 to the 22nd, whereas we're 10 to the 24th. We're 100 times, in that range, more massive. But the moon's got enough mass where it can pull. That's where we get tides, right? It pulls the water up, and there's tides on both sides, which we'll get to in June. We'll spend some time talking about tides. There's land tides and water tides. Anyway, so yeah, that's the main. Here's how usually it goes. You'll see in textbooks, a fly versus a semi-truck, and the question is, does the fly, a semi-truck puts a force on a fly, does a fly put an equal opposite force on the semi-truck? And normally your first impression is no, right? There's no way. But actually it does. The difference is that the fly's got a tiny mass and the truck's got a huge mass. So the truck's hardly going to notice. It's going to be on the order of, nanometers per second. But the fly, it's going to have devastating consequences, because the fly was flying, say one direction at, say, 10 miles an hour. It turns around and goes 70 miles an hour in a matter of a microsecond. So that is a pretty devastating change in velocity. Okay, so that's it for all that stuff. These are all the different classes that talked about it. Okay. All right, there we go. The next thing we went back over again was this idea of a non-inertial frame of reference. Right now, if you're going to decide to go to California and chuck it all, and going to leave Norman, say this summer for some crazy reason, some Jack Kerouac on the road, so you jump on a boxcar, and then you fall asleep. You shut the door, you fall asleep, and you notice before you fell asleep there was this weird hanging uh, ring on the ceiling. He thought that was strange. And then you wake up, and when you wake up at whatever later on that day, you notice that it looks like that it's gone from here to here, and you conclude that there has to be ghosts in there with you, because at that point you are in a non-inertial frame of reference, meaning that the frame of reference you're in is accelerating. And if you don't know it's accelerating, you're going to think there's all these phantom forces that are causing things to do this. You're going to think there's ghosts causing that to go at that weird angle. Well, in reality, when you step back and look at it from a hill, outside the train, you notice, wait a minute, it's actually this turns it back into an inertial frame of reference, where you're sitting is not accelerating. Then you can look at it and say, okay, I see that the whole train is accelerating to the left. Therefore, that ball is moving back to the right. We talked about you driving around at lunch and doing this, which you ought to do. You can actually determine how fast you're going, like by how much, what an angle or how fast you're accelerating by what an angle you have there. Once you get to your speed, that thing will go back to vertical. Whatever they have hanging on your rear mirror will go back to vertical. You don't feel velocity. You only feel acceleration, and you feel acceleration because F equals ma. Because acceleration begats a force. Well, a force begats acceleration. But if you're accelerating, there must be some kind of unbalanced force on you, and that's what you're feeling. Okay. Or you're feeling the resistance of your body to that force. You're feeling the inertia. Okay. So enough of that. Let's keep going. Oh, and then we talked about elevators. And we talked about elevators yesterday, but we kind of worked on that some more today. Elevators, you could spend probably a week on elevators in physics, because so much physicists love elevators because they are their own frame of reference, and you can move an elevator around and turn it into a non-inertial frame of reference. So you'll always see physics problems where they're all contrived. There's a spring hanging from the ceiling of an elevator, and then the elevator. Okay, so all that kind of stuff. These weird questions, but that's because they can manipulate it and make it accelerate. All right. So if you're standing on a scale, on an elevator, an analog scale, say you weigh 180 pounds, when you hit the up button, all of a sudden you gain up to 200 pounds. On average, you gain about 20 pounds, and that takes about a second and a half for a notice to cause that to happen. Doesn't last long. You'll see the analog scale spike up, and then it'll come back down again. Okay. So your normal weight is, here we go. So normally you have a mg down on you and then an ns up, and ns means scale, the normal force from the scale. And so normally those are congruent to each other. But when you hit the up button, see, normally you have n minus mg equals 0 because it's static. But when you hit the up button, you have an acceleration. And so now you have n minus mg equals, your whole frame of reference is accelerating. So if you didn't realize you're accelerating, you go, oh my God, I just gained 20 pounds. What is wrong with me? And then it would go away again. You go, oh, shoot, that was a close one. Better go to the doctor. So it's, you know what I'm saying? But so that's the idea of a non-inertial frame of reference. Okay. So we talked about it. If you're on the fifth floor and you push the down button, push the first floor button, you won't gain weight. You'll lose weight, but you'll lose like 20 pounds apparently. And here is the equation that runs that. It's basically the same equation I just showed you. Just pull the m out, made it a little fancier. I'll put this on equation sheet number 17. But that NS is the reading. That's what the scale shows in pounds or in newtons. And then the mass of the person, that's in kilograms or slugs. And then the G is either 9.81 or 32.2. And the acceleration is positive if you're rising, negative if you're falling. Okay. If you fall at 9.81, therefore there is no scale reading, right? At that point, because it's G minus G. Okay. If you're rising at 9.81, you're going to feel like you weigh twice what you weigh. So I'm going to feel like I weigh 400 pounds if I could get something to accelerate that quickly upwards. Okay, so then we talked, this all leads to Einstein. Well, let's just keep going. I mean, there's from a couple years ago. There's all the, I'll put this in there. That's all that stuff filled out. We talked about all that in discussion. And then I'll put this lecture on there when I get a chance this weekend. But I want to talk about Einstein. Now, at this point in class, I showed this 2-minute video. This is from this series called the Genius series. It's on right now. It was on Nat Geo. Now it's on HBO Max. So if you have HBO Max, you should watch it. The first season is about Einstein and Mileva, his wife. It's really good on Mileva. So really, it shows a lot about her too. She's a brilliant, interesting person. So if you get a chance, you ought to watch it. It's a good, once a week or so. But it's more drama. I mean, it's not just equations. There's not that much of it. There's no math in it really. It's more of a kind of explaining Einstein. So anyway, my sister lives just outside Zurich. We went to this place around where Einstein lectured. We also went on the balcony. I didn't realize it at first, but I looked around and said, "Oh my God, this is the balcony that Einstein figured out." I think it was either here or Bern, but it looks like the one that I've seen in pictures. It's the balcony that he figured out special relativity with clocks, looking at clock towers. Anyway, so this movie, like I say, I'll put the clip in the comments, but this is where he first had what Einstein called his happiest thought. And it is basically this, and we talked about it in class. What if you cut the cable? Say you're on the Devon Tower, you're up there at the restaurant, you get done, you come back out, you get on the elevator, and then the cable snaps. Then you are going to fall right. You're going to fall as fast. You are going to fall as fast as the if you're in free fall, as fast as the elevator is. And the elevators, everything falls at the same rate. We determined that, way back in October. Basketballs, tennis balls, everything falls at the same rate. We watched the Brian Cox video. Bowling ball and feather fall at the same rate in a vacuum. So everything pretty much falls at the same rate here. So if you were in that elevator, the question is, what would happen to you? And the idea is you would float, right? You're going to float inside that elevator. Everything around you will float. The scale will float. Your phone will float. Everything's going to float for, a few seconds until you hit the ground. Not a bad way to go. I was suggesting maybe we make a 90-story shaft. And then anybody that wants to, once they turn about 90, where they're pretty much done with most of their life, they can get in that shaft, get in an elevator, and then we just snap the cable. And they come down, they get to float. It'd be kind of cool. It's like you got, okay, I got that to look forward to. When I'm 90, I get to float for a while. And then it's over, like boom, like that. Okay. Anyway, that was my idea. I don't know if it'll make much money, but I think you'd be doing a service to 90-year-olds. Okay. I feel about 90 today. All right. So forget that. So we talked about the idea of floating. And Einstein, in this clip, this is where he had his happiest thought. He said, if we are all floating in that elevator, then, or if I rise in the elevator really quickly, I'm going to feel heavier. You know, he's basically going through the elevator equation. But he goes, then what is gravity? What is gravity? Gravity, basically, if I'm falling, I don't feel gravity anymore. If I'm falling in that elevator, I've totally lost the ability to feel gravity. I don't feel myself falling. So he said, you know, gravity's not a force. How can a force just go away depending on your circumstances? That doesn't happen with strong nuclear force. You know, that's holds the gluons, those gluons between the, you know, subnuclear particles. It doesn't affect strong nuclear force. It's not dependent on the situation. Electromagnetism, positive, negative attraction, you know, like charges repel, that doesn't depend on the situation. Maxwell's equations. How about weak nuclear radio involving beta decay, those radioactivities? That doesn't depend on the situation. You can't manipulate the situation and make that go away. Only with gravity can you do that. And so Einstein said, you know what I'm thinking? Gravity is not really a force. Gravity is simply equivalent to acceleration. And so, or the effects. The effects of gravity are the same as the effects of acceleration. And this is called the principle of equivalence. It was Einstein's happiest thought. So there it is written out. I'll show it to you in more graphic form here in a second. But um, that's that's this idea. That's what let him down. He had this thought after he had special relativity. So now we're looking in the 1906, 1907 range. He'd already 1905 was his miracle year. So he'd already published the papers on easy MC squared. He published that at the end of the year. He published like 5 extremely important papers. But E is equal to MC squared was just the last of them, which, by the way, he did not win a Nobel Prize for. He won it for the photoelectric effect, which he published also that year, which started our road down to quantum mechanics. Anyway, so this came later. He was fighting a guy named Minkowski, and he was having trouble with the math. It took him 10 years to get from special relativity to general relativity. And I think that Minkowski would have gotten there within a year or two. He was like right behind Einstein. But one thing he had more math. He had more math skills than Einstein, but didn't have the imagination Einstein. He couldn't do the gedunks. He couldn't do those deep thought experiments that Einstein could do. So here's a little. Let's do another gedonks here today. Here we go. All right. So we have this box. Let's say I have this box, and on the box I have rockets. Okay. So I have an endless supply of energy down here at the bottom of my box. So I can do the old thrust equation. I can send this thing anywhere I want. Let's say that it goes really fast and I get out to interstellar space. And then I'm worn out. Okay, I finally get a chance to catch a break. People aren't bugging me all the time. You know, not that I get bugged, but I mean, let's just say for the scenario here. So this person falls asleep. Okay. Great. So he's floating around interstellar space, meaning that there's no star close. And then some aliens come along and they decide to pull a prank. So they hook up cables to the top of this rocket box. And then they attach that to their spaceship. So force of thrust. They thrust they run the engines so that the acceleration, they have it in time, they have it all computerized. The acceleration is 9.81 meters per second squared. Now and I asked the students, what's going to happen to you? Well, you're going to be kind of you'll be now lying on the floor because the whole thing is accelerating quote upward. So here you are, you're lying on the floor now, and you wake up and you're very excited because you think, hey, you think I'm on Earth, right? I'm on Earth. So you get all excited. You fling open the door. You exposing yourself to the vacuum of empty space. Everything, including you, is sucked out. I'm sure your innards are probably popped through your stomach because you got a pressure problem. But you wouldn't last long. Okay, so that, and then of course the aliens are, they think it's hilarious. They pranked you. Okay, so here it is in another form. If you are experiencing gravity on Earth, this formula right here is Newton's universal law of gravitation. That'll be I think the first formula we tackle in June. We're going to get into gravity in June, and that's like our first lesson. And so we'll tackle this formula a little bit, and I'll show a demonstration, that kind of thing. All right, so that's you weighing, let's say 150 pounds. Okay, mg. Well, you're out in interstellar space. You can achieve the same thing, what you apparent weight of 150 pounds, but it's apparent. It's not real. Well, what do we think? Why do we think that what we're experiencing is real? It's kind of weird. You always think, well, the other situation's apparent. Well, maybe your situation's apparent. All right. So what Einstein's saying is there's no difference between the effects of gravity or the effects of acceleration. And that seems kind of cool. It's a huge leap, but it led to general theory of relativity. By the way, this means, like an equal sign, that means numerically these two sides are equal. This means equivalent to, not equilibrant, equivalent. So equivalent to, three little lines like that. It means it's kind of the same conceptually. So that's a good thing to throw out there, those little three lines every once in a while. Okay, and anything else? I think that's about where we ended. There's another one of these, a little nicer, on Earth versus accelerating space. That you still have the same weight. We'll get to that one on Monday. We'll talk about that Monday. Okay, I think we got pretty much all we talked about. There's another one, strong principle of equivalence right there. You think you're back on Earth. Okay, so then we're just about to get to the good stuff, and then the bell rings. So, or actually, all their bells rang, and we did Flashback Friday. All right, I will finish this now, and I'll see you guys Monday.